September 15th, 1944. The rolling fields east of Aachen, Germany. Corporal James Henderson felt the Sherman lurch beneath him as driver Billy Morrison pushed the throttle forward, accelerating to 15 miles per hour across uneven ground. Through his gunsight, Henderson watched the crosshairs bounce wildly over a farmhouse window 600 yards distant where German infantry had been spotted. In any other tank, at this speed, over this terrain, accurate fire would be impossible. The gunner would wait for the tank to halt, for the ground to stop shaking, for the gun barrel to settle before even attempting to engage. But Henderson's hands moved to the firing controls anyway. The gyroscope, spinning at 12,000 revolutions per minute inside the Westinghouse stabilizer, had been running for 20 minutes, maintaining its perfect reference to the horizon. As the Sherman pitched and rolled over the churned earth, as the hull rose and fell with each depression, and mound, the 76mm guns stayed locked on target, compensating automatically for every vertical movement of the chassis. Henderson's finger tightened on the trigger. The gun fired. 600 yards away, the high-explosive shell detonated precisely in the farmhouse window. Before the smoke cleared, Morrison was already accelerating toward the next objective. They hadn't stopped moving. They hadn't needed to. This moment, repeated thousands of times across France, Belgium, and Germany in the final year of the war, represented a revolution in tank warfare that military historians would spend decades trying to understand. American tank crews were hitting targets while moving at speeds that made accurate fire theoretically impossible. They were engaging enemy armor at ranges where stationary German tanks should have held every advantage. They were firing the instant they came around corners, within seconds of stopping, with an accuracy that violated everything the Wehrmacht understood about armored combat. The Germans, whose Panther and Tiger tanks possessed superior guns and thicker armor, whose crews had been trained according to the most advanced armored warfare doctrine in the world, found themselves consistently losing engagements they should have won. The explanation wasn't American bravery, though that was real. It wasn't numerical superiority, though that mattered. It wasn't even the much-debated question of armor thickness or gun penetration. The answer lay in a spinning gyroscope, a hydraulic pump, and a fundamental difference in tactical philosophy that American tankers had discovered mostly by accident, refined through desperate necessity, and turned into the deadliest advantage of the tank war. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. November 1941. The Rock Island Arsenal, Illinois. Engineers from Westinghouse Corporation stood in a testing facility, watching the first production model M3 medium tank equipped with their stabilization system. The concept was simple in theory, nearly impossible in execution. Use a gyroscope as a reference point for true vertical. When the tank's hull moved, measure that movement against the gyroscope's stable reference. Feed that measurement into a hydraulic system that would automatically adjust the gun's elevation to compensate. Keep the gun pointed at the same spot in space, regardless of what the tank beneath it was doing. The technology had been developed for naval gunnery, where ships rolling in heavy seas needed to keep their guns level to the horizon. Adapting it to tanks presented entirely new challenges. Naval guns moved slowly, predictably, in 2 dimensions. Tanks moved violently, unpredictably, in 3 dimensions across terrain that could change from smooth road to shell-cratered field in seconds. The gyroscope at the heart of the system spun at 12,000 revolutions per minute, powered by a 400 Hz, 3-phase electrical supply generated by the tank's own systems. At that rotational speed, the gyroscope possessed enough angular momentum to resist any attempt to change its orientation, maintaining a perfect reference to vertical, even when the tank pitched, rolled, or yawed beneath it. When the tank's gun mount moved away from the gyroscope's reference plane, sensors detected the deviation and sent signals to a hydraulic motor. That motor, drawing power from the same hydraulic pump that traversed the turret, adjusted the gun's elevation to bring it back into alignment with the gyroscope's vertical reference. The entire correction cycle happened automatically, continuously, dozens of times per second. On paper, the system could maintain gun alignment to within a few mils of arc, while the tank moved at speeds up to 15 miles per hour over moderately rough terrain. In practice, making it work required precision manufacturing, careful maintenance, and crews who understood how to work with the system rather than fighting against it. The stabilizer that entered production in November 1941 was installed on every M3 medium tank, then on every variant of the M4 Sherman, except those mounting the 105mm howitzer. By the time American armor reached Europe in 1944, tens of thousands of Sherman tanks carried this revolutionary technology. Most crews had no idea how to use it. June 1943. Camp Campbell, Kentucky. Lieutenant Robert Crane stood in a classroom full of newly assigned tank commanders, trying to explain the gyro stabilizer to men who looked increasingly confused and skeptical. The manual classified the system as confidential. Training on its operation and maintenance had been inconsistent at best, non-existent at worst. Many units received their tanks with stabilizer systems already installed, but no personnel qualified to set them up properly. The technology was complex. The gyroscope required 3 to 5 minutes of spin-up time before reaching operational speed. During that time, the tank's battery supplied power to an electric motor that brought the gyro to 12,000 RPM. If a crew turned on the stabilizer and immediately tried to use it, the gyroscope lacked sufficient angular momentum and the system would hunt violently, oscillating around the target rather than locking on. Gunners who experienced this hunting effect assumed the stabilizer was broken or useless and switched it off. The hydraulic system required careful adjustment of something called stiffness, a parameter that controlled how aggressively the system corrected for deviation. Set the stiffness too high, and the system would overcorrect, creating oscillations. Set it too low, and the system couldn't keep up with the tank's motion. Finding the correct setting required expertise that many crews simply didn't possess. The gun had to be properly balanced. If the barrel was heavier on one end than the other, the imbalance would fight against the stabilizer's corrections, causing the system to work harder and wear out faster. The recoil system had to be correctly adjusted. If air entered the hydraulic lines, the cushioning effect would be lost, and the stabilizer couldn't compensate properly for recoil forces. When crews encountered problems with the stabilizer's operation, they often lacked the technical knowledge to diagnose the issue. Was it the gyroscope, the hydraulic pump, the adjustment of stiffness, the gun balance, the recoil system? Without proper training, there was no way to tell. The easiest solution was to disconnect the system entirely and fight the tank the traditional way, with the gunner manually controlling elevation using a handwheel. By mid-1943, a disturbing pattern had emerged across armoured training units. Crews were systematically disabling their stabilizers, removing the fuse that powered the gyroscope, or simply leaving the system turned off during training exercises and combat operations. The reasons varied. Some crews genuinely believed the stabilizer was broken or useless because they'd never seen it work correctly. Others feared that using the classified technology might reveal American capabilities to the enemy if their tank was captured. Still others simply didn't understand what the stabilizer was supposed to do and saw it as an unnecessary complication in an already complex system. This wholesale rejection of the stabilizer reflected a deeper problem in American armored doctrine. The United States Army, in 1943, still operated under the assumption that tanks would almost never fight other tanks. That mission belonged to tank destroyers, the fast-moving, thinly armoured vehicles mounting large guns specifically designed to hunt enemy armour. Tanks would support infantry, destroy fortifications, engage soft targets. The idea that a Sherman might need to engage a Panther or Tiger in direct combat seemed unlikely, almost beside the point. When tank versus tank combat did occur, American doctrine emphasized the same basic principles that had governed armored warfare since the first tanks rolled onto World War I battlefields. Halt, identify the target, aim carefully, fire. Accuracy came from a stable firing platform. Moving targets were difficult to hit. Moving while shooting was nearly impossible. The stabilizer challenged all of these assumptions. It suggested that tanks could fire accurately while moving. It implied that the first shot in a tank duel might not come from a stationary position. It hinted at tactical possibilities that existing doctrine didn't account for. But if crews didn't understand how to use the system, if training was inadequate, if maintenance was poor, then those possibilities would remain theoretical. The stabilizer would be just another complicated piece of equipment that American industry had produced in vast quantities, but that soldiers in the field couldn't or wouldn't use. Then came Normandy. June 24th, 1944. Omaha Beach, France. The 3rd Armoured Division came ashore 18 days after D-Day, grinding up the beach in a steady rain that turned everything to mud. Staff Sergeant Tom McKinley commanded a Sherman M4, a one with the new 76mm gun and a stabilizer system he'd never learned to use properly. His crew had disabled the stabilizer during training at Fort Knox, following the example of other crews in their battalion who'd found the system too complicated and unreliable. McKinley had more immediate concerns. The hedgerow country of Normandy presented terrain unlike anything the division had trained for. Every field was a natural fortress, surrounded by earthen banks 3 to 4 feet high, topped with thick vegetation. German forces had turned every hedgerow into a defensive position, every field into a killing zone. The division's first combat operation came on June 29th at Villiers-Fossard. McKinley's platoon advanced in support of infantry, moving cautiously through lanes cut by engineer teams, equipped with the newly developed hedgerow cutters. The mission was supposed to be straightforward: clear the village, push through to the next objective, maintain momentum. The Germans had other plans. From concealed positions in the hedgerows, 88mm anti-tank guns opened fire at ranges where their high-velocity rounds could penetrate a Sherman's frontal armour before the American crews even knew they were under attack. The German gunners had perfect fields of fire down the narrow lanes between hedgerows. They'd pre-registered their weapons, knew the exact ranges, waited for American tanks to enter the kill zones before firing. McKinley's platoon lost 2 Shermans in the first 10 minutes. Both were hit from positions the crews never spotted. Both burned. The survivors fell back, regrouped, tried again. This time they moved faster, refusing to give the German gunners time to aim carefully. McKinley pushed his driver to keep moving, to never present a stationary target. They came around a hedgerow corner and immediately took fire from a German position 200 yards distant. McKinley gave the fire command. His gunner, Corporal Ed Walsh, tried to engage using the manual controls, hand cranking the elevation wheel while the tank bounced over rough ground. The first shot missed high. Walsh corrected, fired again. This round hit low, striking the earth bank in front of the German position. McKinley could see the 88's crew working frantically to reload, to get off the next shot that would kill his tank. Walsh fired a 3rd time. The round went wide. The German gun fired. The 88mm armour-piercing round struck McKinley's Sherman on the turret front, penetrating the armour and detonating inside the crew, a compartment. McKinley, standing in the commander's position with his head exposed above the turret, was shielded from the worst of the blast, but felt the tank shudder violently. The intercom went dead. Smoke poured from the turret hatches. McKinley gave the immediate order to bail out. All 5 crew members escaped before fire reached the ammunition storage. McKinley's first combat engagement had lasted approximately 15 seconds from first shot to tank loss. His crew had gotten 3 shots off and scored 0 hits while moving. The German crew, firing from a prepared stationary position, had achieved a first-round kill with their 4th shot, compensating for 3 American near misses, while working smoothly through their loading drill. The math was simple and brutal. German guns firing from stationary positions, with carefully prepared fields of fire, were hitting American tanks that couldn't shoot back effectively while moving. This happened again and again across the hedgerow, country. American armour doctrine said to halt before firing, but halting in the open meant presenting a perfect target to German gunners who already had their weapons aimed at likely positions. American armor doctrine said tanks shouldn't fight other tanks or anti-tank guns, but the hedgerows were full of anti-tank guns and American tanks kept encountering them because there weren't enough tank destroyers to handle the mission. American armor doctrine had been written for open terrain, for exploitation and pursuit, for supporting infantry against prepared fortifications. The hedgerows of Normandy violated every assumption that doctrine was built on. Some crews began experimenting. July 1944. Near Saint-Lô, France, Technical Sergeant Mike Patterson had a theory. His battalion had lost 30% of its tanks in 2 weeks of hedgerow fighting. The pattern was consistent. German anti-tank guns engaged from concealment at medium range. American tanks halted to return fire, becoming stationary targets. German gunners, firing from prepared positions with known ranges, achieved high hit rates. American gunners, trying to locate and engage targets under fire while stopped, achieved low hit rates. The side that scored the first accurate hit usually won the engagement. Patterson's theory was that the stabilizer might change this equation. If the stabilizer actually worked the way the manual claimed, it would keep the gun approximately on target while the tank moved. The gunner could acquire the target while moving, refine his aim, and fire within seconds of stopping instead of having to relay the gun completely after the tank halted. That faster engagement time might make the critical difference. The first problem was getting the stabilizer system to work properly. Patterson spent an entire afternoon with his gunner, Corporal Danny Price, studying the technical manual and working through the setup procedure step by step. They balanced the gun carefully, using the equilibrators, the spring-loaded cylinders that counterbalance the barrel's weight. They adjusted the hydraulic recoil system, bleeding air from the lines until the system responded smoothly. They set the stiffness adjustment to the middle position recommended in the manual. They turned on the stabilizer and waited the full 5 minutes for the gyroscope to reach operating speed before attempting to use the system. The difference was immediate and dramatic. With the stabilizer engaged, Price could keep the gun roughly on target even when the tank was moving at 10 miles per hour over uneven ground. The crosshairs still bounced, but they bounced around the target instead of wandering all over the sight picture. When Patterson ordered Morrison to halt, Price could refine his aim and fire within 3 to 4 seconds instead of the 15 to 20 seconds required to relay the gun manually from scratch. Patterson conducted an informal test. He had Morrison drive the tank in, a circle at varying speeds, while Price tracked a stationary target. With the stabilizer off, Price lost the target completely every time the tank hit a bump or depression. With the stabilizer on, Price maintained approximate alignment even over rough ground. The system wasn't accurate enough for firing while actually moving, except maybe at very close range. But it was more than adequate for getting that critically important fast first shot when the tank stopped. Patterson started using the stabilizer in combat. His crew's survival rate and kill rate both improved noticeably. When they came around corners or crested hills, Price already had the gun approximately aimed at likely target locations. When Morrison stopped the tank, Price could engage within seconds. That speed advantage gave Patterson's crew the initiative in engagements where seconds determined who lived and who died. Other crews in the battalion noticed Patterson's success and started asking questions. How did he get a stabilizer to work? What was the secret? Patterson had no secret beyond following the manual's procedures carefully and giving the system time to operate as designed. But that knowledge began spreading through the division. Crews who'd disabled their stabilizers started turning them back on and learning to use them properly. Battalion maintenance officers began conducting classes on stabilizer setup and adjustment. The transformation wasn't instant or universal, but it was real. By August 1944, a significant percentage of 3rd Armored Division tank crews were operating their stabilizers in combat and discovering advantages that training had never revealed. August 1944, the breakout from Normandy. Operation Cobra shattered German defensive lines south of Saint-Lô with the most concentrated bombing campaign in military history. Over 1,500 American heavy bombers and 380 medium bombers dropped nearly 4,000 tons of bombs on German positions in just a few hours. The bombardment pulverized German defenses. Survivors were dazed, disorganized, unable to mount coherent resistance. American armor poured through the gap, racing south into open country. For the first time since landing in France, American tank units operated on terrain that matched their training. Open fields, paved roads, rolling hills instead of the claustrophobic hedgerow maze. The war of movement had begun. German forces attempted to retreat in good order, to establish new defensive lines, to delay the American advance long enough for reinforcements to arrive. But American armor moved too fast. Tank columns raced down roads at 25 miles per hour, covering ground that retreating German infantry couldn't match. When German units attempted to establish blocking positions, American tanks arrived before the defenses were ready and attacked immediately, maintaining momentum that gave the Germans no time to prepare. The pace of operations revealed new advantages for tanks equipped with working stabilizers. In pursuit operations, hesitation meant losing contact with the enemy. Speed meant catching German units before they could escape or dig in. Tanks that could engage targets quickly, without lengthy stops to aim carefully, maintained better tempo than tanks that had to halt completely for every engagement. Sherman crews who'd learned to use their stabilizers effectively found they could spot a target, track it while moving, then stop briefly, refine aim, fire, and accelerate again in a matter of seconds. Crews without working stabilizers, or without the training to use them effectively, required longer stops and more time to get accurate fire, sacrificing the momentum that pursuit operations required. The difference became obvious in after-action reports. Tank platoons with high stabilizer usage rates reported more enemy vehicles destroyed per tank loss than platoons with low stabilizer usage rates. They also reported shorter engagement times and better ability to maintain pursuit tempo. The correlation wasn't perfect. Casualty rates and success rates depended on many factors, but the trend was clear enough that division leadership started emphasizing stabilizer training and maintenance. By September 1944, American armored doctrine was evolving in real time based on lessons learned in combat. Official doctrine still said tanks shouldn't fight other tanks. Reality said they fought other tanks constantly because the battlefield didn't conform to doctrinal assumptions. Official doctrine said fire from a stationary position for best accuracy. Reality said stationary tanks died faster than moving tanks when German anti-tank guns dominated the battlefield. The stabilizer offered a way to reconcile these contradictions. It allowed relatively accurate fire after brief halts instead of extended ones. It maintained approximate aim while moving, dramatically reducing the time needed to engage after stopping. It gave American crews a speed advantage in target engagement that partially compensated for German advantages in gun range and armor penetration. September 1944. The German border. 3rd Armored Division approached the Siegfried Line, Germany's western defensive fortifications. The pursuit across France had carried American armor 300 miles in less than a month. Now the advance slowed as German resistance stiffened. The Wehrmacht was fighting for German soil now, not occupied France. Every field, every village, every hill was defended with desperation that the retreat across France hadn't shown. American tank crews faced a new challenge. German tanks, Panthers and Tigers, appeared in greater numbers. These were not the second-line Panzer IVs and Sturmgeschütz assault guns that had been common in France. These were first-line machines with guns that could penetrate Sherman armor at ranges exceeding 2,000 yards, far beyond the effective range of even the Sherman's 76mm gun against frontal armor. The technical disadvantage was real and severe. A Panther could kill a Sherman from distances where the Sherman's rounds would bounce harmlessly off the Panther's sloped frontal armor. A Tiger was nearly impervious to frontal attack at any range. American crews facing these vehicles in open country engagements understood they were outmatched in armor and firepower. German tactical doctrine emphasized these advantages. Panther and Tiger crews were trained to engage at long range, using their superior optics and powerful guns to destroy American tanks before the Americans could close to effective range. German tank commanders favored defensive positions that maximized standoff distance, hull-down positions that exposed only the heavily armored turret, carefully selected firing positions that provided concealment and protected withdrawal routes. This doctrine worked brilliantly when German tanks could establish prepared positions and engage American armor as it advanced across open ground. At ranges exceeding 1,000 yards, Panthers and Tigers were nearly invincible. Their long guns could penetrate Sherman armor, while Sherman return fire had minimal effect. But the doctrine had a critical weakness that American tank crews were beginning to exploit. German tanks had to stop to fire accurately. Panther and Tiger guns lacked stabilization of any kind. The gunner aimed using a manual elevation wheel, dependent on a steady platform for accurate fire. When a German tank moved, its gun bounced with every bump and depression. The gunner lost his sight picture completely. He had to re-aim from scratch once the tank halted. This meant German tanks engaged from stationary positions or, if moving, had to come to a complete stop before firing. The superior German guns and optics couldn't compensate for the loss of situational awareness and engagement speed that resulted from this tactical necessity. American Sherman crews with working stabilizers operated differently. They could move at 15 miles per hour and maintain approximate aim on potential target locations. When targets appeared, the Sherman could engage within seconds of stopping, or in some circumstances, while still moving at slow speeds. The stabilizer gave American tanks a tactical tempo that German doctrine couldn't match. This tempo advantage became decisive in meeting engagements, those chaotic encounters where neither side had prepared positions and both had to acquire targets and engage quickly. In these situations, the side that could fire first, accurately, usually won. Sherman crews with working stabilizers frequently achieved that critical first shot. October 1944. Near Aachen, Germany, 2nd Lieutenant James Cooper commanded a platoon of 5 Sherman tanks, 4 with 76mm guns, 1 with the older 75. Every tank in his platoon had a working, properly adjusted stabilizer system. Cooper had made stabilizer training a priority after watching 3 tanks from another platoon burn in a meeting engagement where German Panthers had halted first and gotten off accurate shots before the American crews could return. Fire. The mission was reconnaissance in force toward a village that intelligence reported as lightly defended. Cooper's platoon advanced in column along a sunken road, 2nd tank in the company formation. At 1400 hours, as the lead tank rounded a sharp bend, it came face to face with a German Panther at a range of approximately 200 yards. Both tanks were moving at moderate speed. Neither had prepared positions. Both crews were surprised. The engagement that followed lasted 12 seconds and illustrated everything that American crews had learned about stabilizer employment. The lead Sherman's commander, Sergeant Paul Mitchell, saw the Panther first by perhaps half a second. Mitchell's gunner, with stabilizer engaged, already had the gun roughly level despite the tank's movement. Mitchell gave the fire command. Gunner, Sabot, Panther, front. The gunner, Corporal Tim Bradley, had been tracking down the road centerline at chest height, the most likely position for a target. When the Panther appeared, Bradley's crosshairs were already approximately on target. He made a minor correction for windage, let the tank's movement settle for perhaps 1 second, and fired while the Sherman was still rolling at 5 miles per hour. The 76mm armor-piercing round struck the Panther's gun mantlet, a weak point in the frontal armor. The round penetrated, detonating inside the turret. The German crew never got a shot off. The Panther's gunner had lost his sight picture the moment the tank came around the curve. He needed 10 to 15 seconds to reacquire the target and aim manually. Bradley needed less than 2 seconds because his stabilizer had kept the gun approximately aimed throughout the movement. That 10-second delta between the time required for a stabilized gun to engage versus an unstabilized gun determined the outcome. The Sherman fired first, hit first, and eliminated the Panther before it could return fire. This pattern repeated throughout the final months of 1944. American crews with working stabilizers achieved higher survival rates and better kill ratios than crews without stabilizers, even when facing technically superior German armor. The advantage wasn't overwhelming. Panthers and Tigers still killed many Shermans in situations where German advantages in gun range and armor penetration proved decisive. But in meeting engagements, in fluid situations where both sides had to acquire and engage quickly, the stabilizer gave American crews an edge that frequently determined the outcome. German intelligence officers captured documents from knocked-out American tanks and examined the stabilizer systems. German engineers studied the technology, concluded it was too complex for German industry to produce in wartime. The precision gyroscopes, the hydraulic systems, the electrical components all required manufacturing capabilities that Allied bombing had destroyed or disrupted. German armored forces would fight without stabilization for the rest of the war. American crews, meanwhile, continued to refine their techniques. November 1944, Hurtgen Forest. The 3rd Armored Division fought in some of the worst terrain of the entire European campaign. Dense forest, steep hills, roads that became mudslides in constant rain. The forest canopy prevented air support. The close terrain negated range advantages and made every encounter happen at point-blank distances. In these conditions, the tank that could fire first won. German forces defended the forest with extensive preparation. Every road was covered by anti-tank guns. Every clearing had pre-registered mortar and artillery concentrations. Every hill crest was a potential ambush site. American armor advanced slowly, taking heavy casualties, fighting for every 100 yards. The stabilizer became even more valuable in the forest. Visibility was measured in tens of yards, not hundreds. Targets appeared suddenly and had to be engaged immediately. Crews with working stabilizers could keep their guns roughly aimed at likely threat locations, head of column, junctions, defiles, while moving through the dense woods. When threats materialized, they could engage within seconds. Crews without stabilizers, or without the skill to use them properly, required longer to relay their guns after each movement. In the forest, those extra seconds frequently meant the difference between killing and being killed. After-action reports from Hurtgen Forest confirmed what had become obvious to anyone paying attention. Stabilizer-equipped tanks with properly trained crews achieved better combat performance than tanks with disabled stabilizers or poorly trained crews. The advantage wasn't absolute. Plenty of tanks with working stabilizers were still destroyed by German fire. But the statistics were clear enough that division leadership issued formal guidance requiring all tank crews to operate stabilizers in combat unless mechanical failure prevented it. By December 1944, American armored doctrine had evolved dramatically from the principles taught at Fort Knox in 1943. Official field manuals still emphasized firing from stationary positions. They still stated that firing while moving was inaccurate and wasteful of ammunition. But combat experience had written new doctrine in blood and fire across 5 months of fighting. The new unofficial doctrine said this: move fast, fire fast. Never give the enemy time to prepare. Use the stabilizer to maintain approximate aim while moving. When contact is imminent, have the gun pointed at the most likely threat location before the threat appears. Stop only long enough to refine aim and fire, then move again immediately. Accept lower accuracy per shot in exchange for higher tempo and better survivability. Close the range aggressively to negate German advantages in gun power and armor thickness. Make the battle happen at distances where American advantages in crew training, mechanical reliability, and gun stabilization could overcome German technical superiority. This doctrine wasn't written in any manual. It emerged organically from crews who learned to survive by adapting their tactics to the weapons they actually had, rather than the weapons doctrine assumed they should have. The Battle of the Bulge tested these lessons under the worst possible conditions. December 16th, 1944. The Ardennes. Hitler launched his last major offensive in the West, sending 3 armies through the Ardennes forest in a desperate attempt to split Allied forces and recapture the port of Antwerp. The German offensive achieved complete surprise. American forces, thinly spread across a sector considered quiet, were overrun in the initial assault. Thousands of American soldiers were killed, wounded, or captured in the first hours. But the German advance began slowing almost immediately. American units, while forced to retreat, fought delaying actions that consumed time and fuel the German timetable couldn't afford. Small groups of American tanks, often outnumbered and outgunned, engaged German armour in meeting engagements across the snowbound roads of Belgium. These engagements, fought in terrible weather over frozen ground with poor visibility, tested crew skill more than technical specifications. Staff Sergeant Tom Holland commanded a Sherman from 3rd Armoured Division's 32nd Armoured Regiment. His battalion had been rushed south to help contain the German breakthrough. On December 20th, Holland's platoon encountered a German column near Hotten, Belgium. 2 Panthers and 3 trucks carrying infantry were moving west, along a narrow road bounded by thick woods. Holland's platoon had 5 Shermans. On paper, this should have been a losing fight. 2 Panthers with 80mm frontal armour and 75mm high-velocity guns against 5 Shermans with weaker guns and thinner armour. German doctrine would say the Panthers should halt, take hull-down positions if possible, engage the Shermans at maximum effective range. But the Panthers didn't halt. The German column was behind schedule, under orders to maintain momentum, racing to reach objectives before American reinforcements could arrive. The Panther commanders decided to push through rather than engage. It was a tactical decision that made sense given their orders and the situation. It was also a fatal mistake. Holland's gunner, Corporal Mike Santos, had his stabilizer engaged and his gun aimed down the road at approximately chest height. When the lead Panther came into view at 400 yards, Santos already had crosshairs on target. Holland gave the fire command. Santos made a slight windage correction and fired, while the Sherman was still moving at approximately 8 miles per hour. The 76mm armour-piercing round struck the Panther's side armour, much thinner than the frontal plate. The round penetrated, causing catastrophic internal damage. The Panther lurched to a halt, blocking the road. The second Panther, following close behind, tried to reverse but couldn't manoeuvre in the narrow space between the burning lead tank and the woods. Holland's second Sherman fired, hitting the stationary Panther in the side. The German crew bailed out seconds before ammunition exploded. The entire engagement lasted perhaps 20 seconds. 2 Panthers destroyed, German column stopped, American platoon suffered 0 losses. This pattern repeated across the Bulge. German armour, operating under pressure to maintain schedule, frequently engaged American tanks in meeting encounters where neither side had prepared positions. In these situations, the side that could fire first and accurately usually won. Sherman crews with working stabilizers won those races more often than German crews with unstabilized guns, despite German technical advantages. The statistics were stark. During the Bulge fighting, American tank destroyer battalions equipped with M36 tank destroyers mounting 90mm guns claimed large numbers of German tank kills. But Sherman battalions, equipped with supposedly inferior 76mm guns, achieved nearly comparable kill ratios when fighting from prepared positions or in meeting engagements. The Sherman's stabilizer, combined with aggressive American tactics and superior crew training, compensated substantially for the technical inferiority of the gun. German after-action reports from the Bulge noted with frustration that American tanks were engaging more quickly than German doctrine predicted. Several reports specifically mentioned American tanks firing accurately within seconds of stopping, sometimes while still moving slowly. German intelligence couldn't fully explain this capability because they lacked the context to understand how stabilization technology changed tactical tempo. January 1945. The weather cleared. Allied air power returned with devastating effect. The German offensive collapsed. American forces counterattacked, pushing German units back toward the Rhine. The final months of the war saw American armor advancing deep into Germany against increasingly desperate but still dangerous resistance. By this point, virtually every Sherman crew in the European theatre had learned to use the stabilizer effectively. The technology that had been classified, mysterious, often disabled in 1943, was now standard operating procedure. Crews understood the setup requirements. They knew the 3 to 5 minute gyroscope spin-up time. They performed the careful balancing and adjustment procedures. They operated the system continuously in combat. The tactical advantages had become impossible to ignore. Field Manual 17-12, the official tank gunnery manual, would eventually be revised to reflect combat experience. The revision, published after the war, stated that tanks equipped with gyrostabilizers were more effective at engaging targets while moving at speeds up to 10 miles per hour. This was a dramatic departure from the original manual's insistence that firing while moving was inaccurate and wasteful, but even this official acknowledgement understated the true advantage. The stabilizer's primary benefit wasn't firing while moving, though that was possible at short ranges. The primary benefit was drastically reduced engagement time after stopping. A Sherman crew with a working stabilizer could engage targets 3 to 5 times faster than a crew with an unstabilized gun. In combat, where the first accurate shot usually determined the outcome, that speed advantage was often decisive. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. March 1945. The Rhine crossings. American armor poured across the river on hastily constructed bridges, exploiting the collapse of German defensive lines. The 3rd Armored Division raced east toward the Elbe River, covering ground at speeds that matched the pursuit across France 8 months earlier. But this time, German resistance was fragmentary. The Wehrmacht was collapsing. Fuel shortages immobilized German armor. Ammunition was scarce. Trained crews were scarcer. The Panthers and Tigers that had seemed so formidable in Normandy were now frequently abandoned by their crews when mechanical failures occurred, because repair was impossible and retreat on foot offered better survival odds than staying with a dead tank. American tank columns encountered these abandoned Panthers and Tigers regularly. Crews examined them with professional interest, noting the impressive guns, the thick armor, the sophisticated design, but they also noted the broken final drives, the burnt-out engines, the empty fuel tanks. Technical superiority meant nothing when the tank couldn't move or fight. The final weeks of the war saw American armor ranging across Germany with minimal opposition. When resistance occurred, it was usually brief and one-sided. German units that tried to fight were overwhelmed by American firepower, air support, and artillery. Units that surrendered were processed and sent to PIO camps. The tank war in Europe ended not with a climactic final battle, but with the gradual dissolution of German military resistance. May 8, 1945. Victory in Europe. The 3rd Armored Division had fought from Normandy to central Germany, covering over 1,000 miles in 11 months of combat. The division had destroyed hundreds of German tanks, thousands of other vehicles, had inflicted casualties far exceeding those it suffered. The division's tank crews had proven that aggressive tactics, superior training, mechanical reliability, and technological advantages like gun stabilization could overcome technical inferiority in armor and firepower. The lessons learned during the campaign would shape American armored doctrine for decades. The importance of crew training, the value of mechanical reliability, the necessity of engaging quickly rather than perfectly, the advantage of maintaining tempo and initiative, and the critical importance of technological systems that enhanced crew capabilities rather than complicating them. The gyrostabilizer exemplified this last principle. It was sophisticated technology that, when properly understood and maintained, made crews more effective. It didn't replace skill. It amplified skill. It didn't guarantee victory. It increased the probability of victory by giving crews an advantage in the critical first seconds of combat. Now, examining the broader technical and tactical context reveals why the stabilizer mattered so much and why German forces couldn't develop an equivalent system. The Westinghouse gyrostabilizer that equipped American Shermans was a single-plane system. It stabilized the gun in elevation only, compensating for the tank's pitching motion as it moved over uneven ground. It did not stabilize azimuth or traverse. The turret still had to be manually controlled or power traversed to track targets horizontally. This limitation meant the system couldn't compensate for the tank turning or for lateral movement. But it didn't need to. The primary source of gun displacement in a moving tank was vertical motion. When the front of the tank dropped into a depression, the gun barrel rose relative to the horizon. When the rear dropped, the gun barrel descended. These pitch movements, repeated continuously as the tank moved over any terrain more complex than a paved road, made accurate fire nearly impossible without stabilization. The gyroscope at the heart of the system provided a stable reference to true vertical. It spun at 12,000 revolutions per minute, fast enough that its angular momentum resisted any attempt to change its orientation. When the tank pitched, the gyroscope maintained its original orientation relative to the horizon. Sensors detected the angular difference between the gyroscope's reference plane and the gun's actual position. This error signal fed into a hydraulic servo system that adjusted the gun's elevation to minimize the error. The system operated in a continuous feedback loop. Measure error, generate correction signal, apply correction, measure remaining error, generate new correction. This loop ran dozens of times per second, continuously adjusting the gun's position to match the gyroscope's stable reference despite the tank's motion. The technology required precision manufacturing that German industry, by 1944, could no longer achieve. The gyroscope had to spin at high speed with minimal friction and perfect balance. The hydraulic system had to respond quickly without hunting or oscillating. The electrical system had to provide stable, high-frequency power. The sensors had to measure angular displacement accurately. All of these components had to work together reliably under the vibration, shock, and temperature extremes of combat conditions. German engineers examined captured stabilizer systems and concluded that replicating the technology was impractical given wartime constraints. The precision ball bearings for the gyroscope were difficult to manufacture. The high-frequency electrical generation required specialized components. The hydraulic servo system needed machining tolerances that German industry, disrupted by Allied bombing and material shortages, couldn't consistently achieve. Even if Germany could have manufactured stabilizers, integrating them into existing tank designs presented challenges. The system required electrical power at 400 Hz, necessitating a specialized generator. It required hydraulic power from the turret traverse system. It required space inside the already cramped turret for the gyroscope assembly and control systems. Retrofitting Panthers and Tigers would have required extensive redesign, so German tanks fought without stabilization throughout the war. This forced German tactical doctrine to emphasize stationary engagements from prepared positions, exploiting the superior range and penetration of German guns, while minimizing the disadvantages of unstabilized fire. This doctrine worked well when German tanks could establish defensive positions and engage approaching American armor at long range. At distances exceeding 1,500 yards, Panthers and Tigers were nearly unbeatable. Their powerful guns could destroy Shermans reliably while Sherman return fire was ineffective against frontal armor. But the doctrine failed in meeting engagements and close-range combat. When neither side had prepared positions, when both tanks were moving and had to acquire targets quickly, the Sherman stabilizer provided a decisive advantage. The German crew had to halt completely, reacquire the target through their optics, manually relay the gun, then fire. This process took 10 to 15 seconds under optimal conditions, longer under stress. The American crew, with a working stabilizer, maintained approximate aim while moving, stopped briefly, refined aim, and fired in 3 to 5 seconds. That speed difference was often the difference between living and dying. The Germans recognized this problem but couldn't solve it. Reports from Panzer crews noted that American tanks seemed to fire more quickly than should be possible. Some reports attributed this to better crew training, which was partially true. American tank crews, by late 1944, were better trained on average than German crews, who increasingly consisted of hastily trained replacements. But the primary factor was technological. The stabilizer gave American crews a genuine, measurable advantage in engagement speed. This advantage was particularly pronounced when firing on the move, though actual fire while moving remained uncommon and was usually ineffective at ranges beyond 200 to 300 yards. The stabilizer kept the gun approximately on target, but approximation wasn't accuracy. The crosshairs still bounced as the tank moved over rough ground. Wind affected the projectile during flight. The ranging was imprecise. All these factors meant that true fire on the move, attempting to hit a target while both the shooter and target were moving, remained very difficult. What the stabilizer enabled was something more subtle but more valuable. It allowed crews to track potential target locations while moving, maintaining situational awareness and approximate aim. When targets appeared, the crew could stop very briefly, perhaps for only 1 or 2 seconds, refine the aim that the stabilizer had maintained, and fire. Then the tank could immediately resume movement. This shoot and scoot tactic proved highly effective. The tank was exposed and stationary for only a few seconds, minimizing vulnerability to enemy return fire. But those few seconds were enough to get an aimed shot off, because the stabilizer had already done most of the work of establishing correct gun elevation during the movement phase. German tanks, lacking stabilization, needed longer halts. The gunner had lost his sight picture completely during movement and had to re-establish it from scratch after stopping. This required 5 to 10 seconds minimum, often longer. During those seconds, the German tank was stationary and vulnerable, and the American tank might already be moving again after firing. The cumulative effect of these tactical tempo differences was substantial. In a series of engagements over a day of combat, Sherman, crews with working stabilizers, could engage more targets in less time with lower exposure than German crews with unstabilized guns. They could maintain better tempo in pursuit or exploitation operations. They could react more quickly to unexpected encounters. All of these advantages, individually small, added up to significantly better combat effectiveness. The question of whether Shermans could hit Panthers at 2,000 yards while moving requires careful examination. 2,000 yards is 1,830 meters, a very long engagement range for World War II tank combat. At this range, several factors made accurate fire extremely difficult. First, the optical magnification of gun sights limited target identification and precise aiming. Sherman gun sights provided roughly 5-power magnification. At 2,000 yards, a Panther would appear in the sight as a small, relatively indistinct target. Identifying it as a Panther rather than some other vehicle required good visibility and an experienced eye. Aiming at a specific part of the target, attempting to hit a weak point or vulnerable component, was nearly impossible at this range. Second, the ballistic drop of the projectile became significant. A 76mm armor-piercing round fired at 2,000 yards would drop considerably during its time of flight, requiring substantial elevation of the gun barrel to compensate. The gunner had to know the correct range precisely and apply the appropriate elevation correction. Range estimation at 2,000 yards was difficult and imprecise with World War II optical rangefinders. Third, any movement of the firing tank introduced additional error. Even with the stabilizer compensating for pitch movements, lateral motion from turning or slewing caused point of aim to shift. Wind affected the projectile during the long flight time. Small errors in aim translated to large misses at extended range. The realistic answer is that Shermans occasionally did fire at long-range targets while moving, and occasionally did hit those targets, but accuracy was very low, and such fire was generally not tactically useful. The stabilizer allowed the gun to remain roughly on target, but rough approximation wasn't accurate enough for reliable hits at extreme range. What the stabilizer did enable was maintaining tactical awareness and approximate aim during movement, so that when the tank stopped, even briefly, accurate fire could be achieved much faster than without stabilization. A Sherman could move at 15 miles per hour while tracking a Panther at 2,000 yards, keeping the gun roughly aimed at the target. When the Sherman stopped, the gunner refined his aim, confirmed range, and fired. The entire engagement from stop to shot could happen in 3 to 4 seconds rather than 15 to 20. That capability, while less dramatic than scoring hits while moving at high speed, was tactically far more valuable. It allowed American tanks to maintain momentum during advances, to close range quickly while maintaining the ability to engage, and to shoot first in meeting engagements. These advantages, exploited consistently across thousands of engagements, contributed substantially to American success in the tank war. The Germans never developed an effective counter to stabilized fire. Their doctrine continued to emphasize long-range engagement from prepared positions, attempting to destroy American tanks before they could close to effective range. This doctrine worked when terrain and tactical situation allowed it. In the open country near Caen in Normandy, in the fields around Aachen, German tanks engaged American armor at maximum range and inflicted heavy casualties. But as the war progressed, American tactical doctrine evolved to minimize German advantages. American tanks used terrain to close range quickly, approaching through cover to negate German range advantages. They used superior numbers, coordinating multiple tanks to attack from different angles simultaneously. They called in artillery and air support to suppress German positions before tanks advanced. They exploited American advantages in mechanical reliability, knowing that German tanks frequently broke down and couldn't be recovered or repaired. By early 1945, the technical superiority of German tanks meant progressively less. A Panther with a broken final drive was worthless. A Tiger without fuel was a stationary pillbox, dangerous if you approached from the front, irrelevant if you bypassed it or attacked from the flank. The sophisticated engineering that made German tanks impressive on paper couldn't compensate for the systemic failures of German logistics, production, and training. The Sherman, by contrast, represented the opposite design philosophy: adequate technical performance in all categories, exceptional reliability and maintainability, producible in massive quantities using available industrial capacity, supportable through long supply lines across oceanic distances, crewable by adequately trained soldiers rather than requiring specialists. The stabilizer fit perfectly into this philosophy. It was sophisticated technology that made crews more effective without requiring specialized training or exceptional maintenance. Once crews understood the basic setup procedures and operating principles, the system worked reliably and provided genuine tactical advantages. The contrast between American and German approaches to tank warfare extended beyond technical specifications to fundamental differences in military culture and doctrine. The German military emphasized technical excellence and individual skill. Their best tank commanders were highly trained professionals who understood armor doctrine thoroughly and executed it skillfully. Their best tanks were engineering masterpieces that incorporated cutting-edge technology and sophisticated design, but this emphasis on excellence created brittleness. When the best tanks broke down, when the best commanders were killed, when fuel and ammunition ran short, German effectiveness collapsed. The system couldn't absorb losses or adapt to degraded conditions. It required optimal circumstances to function as designed. The American military emphasized adequacy and adaptability. American tanks were good enough at everything rather than excellent at specific things. American tank commanders were adequately trained rather than superbly trained, but there were enough of them that losses could be replaced. American logistics provided enough fuel, ammunition, and spare parts to keep the force functioning even under difficult conditions. This approach created resilience. When American tanks were destroyed, new tanks arrived to replace them. When crews were lost, Replacement crews were trained and deployed. When tactics proved ineffective, new tactics were developed and disseminated. The system could absorb tremendous losses and continue functioning, could adapt to changing conditions, could learn from experience and improve. The gyrostabilizer exemplified this adaptive approach. It was technology that enhanced crew effectiveness without requiring the crews to be exceptional. An adequately trained gunner using a stabilizer could achieve engagement speeds that a highly skilled gunner without a stabilizer couldn't match. The technology compensated for limitations in crew skill and experience, raising the baseline effectiveness of average crews. This is what won the tank war. Not superior armor, not more powerful guns, not invincible heavy tanks. Adequate tanks, produced in massive quantities, supported by excellent logistics, crewed by adequately trained soldiers who learned continuously from combat experience and adapted their tactics to exploit the advantages they actually had rather than the advantages doctrine assumed they should have. The gyrostabilizer was one of those advantages. A technology that seemed minor, that many crews initially ignored or disabled, that training barely covered, ultimately proved decisive in thousands of engagements across 11 months of combat. It allowed American tank crews to fire faster, engage more effectively, survive better, and kill more enemy tanks than should have been possible given the technical specifications of the vehicles involved. The legacy of the stabilizer extended far beyond World War II. Post-war American tank development incorporated lessons learned from combat experience. The M46 Patton, entering service in 1949, featured an improved stabilization system. The M47 and M48 Pattons refined the technology further. By the time the M60 entered service in 1960, American tanks featured full two-axis stabilization, compensating for both pitch and yaw, allowing accurate fire while moving at higher speeds. Soviet tank development followed a parallel path. Soviet engineers, studying American stabilizer systems in Lend-Lease Shermans, developed their own stabilization technology. The T-54A, entering service in 1954, featured a two-axis stabilizer that made Soviet tanks competitive with American designs. Chinese and other Soviet-aligned forces adopted similar systems. By the 1960s, gun stabilization was standard in main battle tanks worldwide. Modern tanks feature stabilization systems so sophisticated that they can fire accurately while moving at high speed over rough terrain, engaging targets at ranges exceeding 2 miles. Digital fire control systems compensate automatically for range, target motion, barrel wear, wind, ammunition temperature, and dozens of other variables. The first-generation Westinghouse gyrostabilizer that American tankers struggled to understand in 1943 seems primitive by comparison, but the fundamental principle remains the same. Give the crew tools that enhance their effectiveness. Compensate for human limitations with technology. Allow adequately trained soldiers to achieve results that would otherwise require exceptional skill. The gyrostabilizer pioneered this approach in armored warfare, demonstrating that technological advantages in engagement, speed, and tactical tempo could overcome technical disadvantages in armor protection and gun power. The story of the gyrostabilizer is ultimately a story about adaptation and learning. American armored forces entered combat in 1944 with equipment their crews didn't fully understand and doctrine that didn't match battlefield realities. They suffered heavy losses, learned painful lessons, adapted their tactics, and discovered that seemingly minor technological advantages could be exploited to achieve major operational effects. German armored forces entered the same campaign with superior tanks, experienced crews, and sophisticated doctrine. They inflicted heavy casualties but couldn't prevent their eventual defeat because their advantages required conditions that the battlefield increasingly didn't provide. Their tanks were mechanically unreliable, their logistics were inadequate, their fuel was scarce, their replacement crews were poorly trained. Technical superiority couldn't compensate for systemic failure. The side that could learn, adapt, and exploit the advantages it actually had defeated, the side that remained committed to doctrine that assumed advantages it no longer possessed. The gyro-stabilizer was one small piece of that larger story, a technological capability that American crews learned to exploit effectively, while German forces had no equivalent and no effective counter. In the end, wars are won not by the best equipment, but by the best system. The system that can produce adequate equipment in massive quantities, sustain it across vast distances, crew it with adequately trained soldiers, repair it when damaged, replace it when destroyed, and continuously improve tactics based on battlefield experience. The Sherman tank, including its gyro-stabilizer, represented that kind of system. It wasn't the best tank of World War II by any single metric, but it was good enough, reliable enough, producible enough, and supportable enough to win the tank war decisively. The gyro-stabilizer gave American tank crews an advantage their enemies couldn't match. Not an overwhelming advantage, not an invincible advantage, but a real, measurable, tactically significant advantage that made them faster to engage, more likely to fire first, more capable of maintaining tempo, and more able to survive and kill in the chaotic reality of armored combat. That advantage, combined with American numerical superiority, better logistics, superior crew training systems, more reliable vehicles, and adaptive doctrine, proved decisive. By May 1945, American armor had driven from the beaches of Normandy to central Germany, destroying the Wehrmacht's armored forces and ending the war in Europe. The gyro-stabilizer had played its part in that victory, a technological innovation that changed tank warfare forever and established principles that remain valid in modern armored combat. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.